Hello folks, welcome to Ants Are Everywhere. We're looking at more chip stuff. This is going to be short. I only have about half an hour. I got a late start. I'm also behind on the request video situation. I am aware of that, and I will make up for it with interest once my schedule gets more predictable. I wasn't quite sure where I wanted to be this morning, but I figured OpenCores was a good place to start. They're supposed to have cores of every sort. It's an online community for the development of gateware IP cores. It is the place where such cores are shared and promoted in the spirit of free and open source collaboration. So let's take a look at what they have. Didn't I click on projects? Here we go. We have an arithmetic core, or 119 of them, 42 prototype boards, some communication controllers, coprocessors, crypto core. ECC is probably error correcting codes, probably not elliptic core cryptography. We'll look at it. Memory cores. Does this not work? Can I not open a new tab? I can open the image in a new tab. What kind of world are we living in here? And processors, including some microcontrollers, a 16-bit CPU loosely based on Caxton Foster's Blue architecture, and so on. And what do we want to see? Processor is maybe too fancy for me. Here's a DRAM controller. Here's a CFI flash controller, DDR2, DDR3, a FIFO library. I don't know if that's just a FIFO like Q implementation. A FAT32 parser. FAT32 is a file system. Does that count as a memory core? Let's look at DDR2. Why not? Oh, we have status here. What is WBC? I don't know. But maybe we'll look at this one because it has the done status. And what else do we have? Libraries are probably essential, but I don't know if they're so what I want to look at now. We have a real-time clock. That might be interesting. A random number generator. Sure, why not? ECC, LDPC, configurable Hamming generator. This looks like error correcting codes. PCI Express CRC Verilog file. And how about Reed Solomon? Reed Solomon, I think, is has understandable math. DSP should be what? Digital signal processing. A DDS synthesizer. Double clocked FFT core. Sure, why not? An FFT based FIR filter. FIR is what? I don't know. Finite impulse response. So finite impulse response is probably not what I need. We'll just look at a few of these. Prototype board. I don't know what that means. A butterfly light. A KISS board. A PCI board. Let's look at PCI. Let's look at the Z-Links thing. Communication controllers. I do want to see Ethernet, although I'd like to see one that's done. 1 gig Ethernet DPI. I don't know what DPI is. Deep packet inspection. Sounds very nosy. So they're going to look at the traffic and use it for routing and Ethernet-y decisions. Okay. You know what? I might just open a bunch of these and look more at them tomorrow, depending on how far we get today. Crypto core. I guess, why not? We'll do crypto core. Do we want triple DES? We don't need triple DES. How about AES? AES is a star. an OOCP status. We have mini AES, pipelined AES, and RSA. 2 fish. Okay, this should be enough. This should be enough for our needs. I would kind of like to know what some of these, I guess STAR might be OpenCores certified. OCCP, OpenCores Communist Party. This is probably not what it is. Extinct, Existential, Media Licensing Commerce Partners. This is projects again. Okay, well, I don't know what oh, I see. Fact, project. Downloading files, joining information for developers. I don't know. It's not going to tell me, and I don't have much time. Okay, so we're going to kind of go through these quickly, and then if we see something we like, we'll dig into it more tomorrow, I guess, because I'm streaming tomorrow. All right, so here's the 16-bit DRAM controller. This should be some memory controller. We've got downloads and a bug tracker. How's the bug tracker? It's got no bugs, so it must be. That means it's absolutely perfect. This IP core is that of a small, simple SDRAM controller used to provide a 32-bit pipelined wishbone interface. Wishbone is, of course, a cartoon dog. Like that. Hello, I'm missing the chat. Hey! Welcome, folks. Is this similar to CUDA somehow? That's a good question. And the answer is maybe. So CUDA is about APIs, really. It's about making it easier to write certain kinds of software on these chips that were made for processing graphics. So it's maybe a little bit related to CUDA, but as that kind of programming has become very popular and very lucrative, now I think that the needs of CUDA also inform the graphics, whereas I think before it was like the CUDA was a shim over graphics, over chips that were made to serve the gaming community. And you would think that since I told the chat to stay above everything else, it would always do that. Let's see if it will do that. Okay, there we go. But this would be more for like designing a chip that something like CUDA would run on. These should be descriptions, physical software descriptions of the logic that eventually will be made into a physical chip. And so we have we're back. So forget CUDA for a second. Forget I ever mentioned graphics. We're back at the SDRAM controller, 16 bits. OpenCores is more low level. Yeah, that's right. So OpenCores, I think the premise is that if you were like a chip company, you would be like rating OpenCores the same way that software companies rate open source for free IP. So if you needed like a 16-bit SDRAM that was kind of partially written or mostly written, you would maybe use this and just take the code. And it has some license. Where's the license? I don't know. There must be some licensing. So GPL. So if you take this particular code, I don't know. I guess you'd have to open source the whole chip that you were making. But these are, in theory, things that you could use as starting places for writing hardware, which you normally don't think of something that you write, but you at least start with a description of what it's supposed to be. So the configuration is you can configure the clock speed. I don't really know what the trade-offs are here. Why not just make it the fastest clock speed possible? I assume that since clock speeds have tended to go up over time, that's just been hard to do, but maybe you want to have a slower clock speed because you're making like an arcade game or something, like you're trying to refab or fix an old arcade game that had a slow RAM or something. You have the total SDRAM address width, which is columns plus rows plus banks. So I guess one bank has some number of columns and rows, and then you could have multiple banks. And then you have the number of column bits. And something about read latency. I guess you can configure that. Why? I'm not sure. And the design contains 184 flops. I thought a flop was a floating point operation per second. I don't know if a design can contain flops. And you can synthesize this to bigger than 160 megahertz on C-Link Spartan. I think C-Links is an FPGA. Let's double check this. Holy crap. Can you buy an FPGA for $30? Plus $4 shipping? This must be an outdated one, though. It looks old. Does that look old? Not like this particular specimen is dusty or anything, but it kind of looks like an older PCB. I don't know anything about this stuff. This looks newer. This is about $100. Let's try. Can I go to Alibaba? You can buy $1,000, $113. Here's like a nano FPGA. Cool. What else sells stuff? Newegg? They do different. Yeah, they do different based on the manufacturer, but I just don't know why you would choose a lower clock speed. And then here you can get one for like $300-400 on Newegg. And then if you wanted to go, I guess, why not? Let's go to Amazon. 180-ish to 400. I'd say 400 to 1,000 will definitely buy you an FPGA that's probably acceptable. Let's take this whole thing and since I took the time to log into DeepSeek, let's see if DeepSeek is alive. Here's a description of some Verilog design. Why would you want a slower clock speed? Why not max everything out? And then DeepSeek will think about that for a bit. Okay, but what I really want is I want to be able to take a look at the code, but maybe we'll just kind of look at a few of these descriptions first. Here's the real-time clock. It's the categories library, the languages, Verilog. The design is done, the FPGA is proven, and the specification is done. Is it Wishbone compliant? Yes. It's also GPL, so if you use this, you got to open source your things, I think. We can look that up. This core offers a real-time clock capability to a device. It seems some of these descriptions read like they're not. First of all, there are cat hairs all over my mic thing. They read like they're not written by people whose first language is English. So I don't know where. That's not 100% obvious. It's just a kind of feeling I get. I'm wondering where most of these people are based. This is the maintainer, Dan Gisselquist. He's in Virginia. That doesn't necessarily mean he wrote this original description, but maybe he is. Okay. Where did it go? All right, this is the SDRAM. We have GPS schooling. A version of this clock is available that can be GPS schooled. By this, I mean that I have taken the PPS output of whatever the Digilent PMOD GPS board and used it to adjust the full speed and phase of the clock in a separate module. This now accepts the outputs of the GPS time tracking circuit and locks its sub-second resolution to it. So I'm guessing this says it can be used possibly with some modifications as a real-time enough clock for global positioning system. Yeah, what else do we have? We have this random number generator. It's a combination of 3 Talsworth generators. I don't know what a Talsworth generator is. The functions will not synthesize. What does that mean? A VHDL test bench environment. So these are for, I guess, testing VHDL stuff, but they'll not synthesize, so you can't create a physical design based on them. I don't know. List of random number generators. If it's that old, then it's not a generator you would want to use. Hugely influential design. It's a linear feedback shift register. And these are very simple. And I guess it makes sense why this would be a hardware one. Where's Talsworth? 1965. We might as well look at this paper. It's not going to parse. You'd have to like OCR it because it's got a fancy 1960s font. Okay, so if this is not something we can synthesize, does that mean we shouldn't look at it? I'm not sure. Here's the Reed-Solomon encoder. The RTL is done. That's the like Verilog part. We'll upload soon. Does that mean we can't download it? Whatever page 2 is. Language, empty block. Okay. So these are synthesizable IP cores, compatible with whatever these things are, some standards. G709 standard. I'm learning something from all this, even though I'm not seeing the code yet. So G709 looks like it's internet stuff. Maybe over optical networks, optical network. Okay, so I guess you need Reed-Solomon encoding for stuff. If you're going to transmit stuff, you need error correcting codes, so maybe it's part of the standard. Here's the FFT core. For an FFT that runs in a pipeline fashion at 2 samples per clock, a C++ program will generate the Verilog files, allowing the FFT to be of an arbitrary length subject only to the capability of the FPGA used to implement the FFT. And I'm guessing, now that I'm thinking about it, that the reason you might not want to fully max out everything on your SDRAM controller is you might have something like an FPGA where you are, you just have constraints of all of the things you can put in. And so sometimes you need to use those constraints to take from one core and give it to another or something. Why would I need an FFT that runs at 2 samples per clock? Let me remind them that FFTs tend to use their multiples more efficiently than other filtering implementations. But to do so, you need to use some form of overlap and add filtering structure. An overlap and add structure immediately puts you into needing an FFT that runs at twice the clock speed of the incoming data. Okay. And so here's some description of the different FFT sizes and the bit widths and the twiddle factor bits and so on. Block RAMs and so on and so forth. LSFR actually has 2 versions though, Galois and Fibonacci. Old but effective. Cool. Galois, I assume, is group theory based. I don't know what Fibonacci is. What is going on here? Some sort of graphics nonsense. That's why I'm taking this off, because I don't trust the whatever's going on graphically with my computer right now. Here's some PCI board. It's small but versatile, using Spartan 2 at 200K gates. There's an image. Can we see it? We have news. No bugs. Good. No, just kidding. No bugs is probably a bad sign. Here's some schematic. Since this is a PCI board. I don't have permissions. I need to log in. Okay, so maybe I can't read any of this stuff without permissions. In fact, let's see if I can download anything. We have a bunch of images. Here's the PCI, some other thing. Here's a low-cost PCI board with Z-links something or other. It looks like that. You can attach it with your ribbon cable. And it says a TOS link, fiber optic receive and transmit for something. TOS link is networking, right? Optical fiber connector. Is this old? Designed in 1983. So I think all of these OpenCore stuffs are old. We have a 4-volt bus switch supply, a 20-pin I/O expansion, some user LEDs, programming cable. I guess that's you plug it in and program it and debug it. Oh, this is the FPGA, I think. Okay. Cool. And here's the Ethernet thing, but I'm not sure that I get to see any of the code. Oh, I can download it. Oh, I can browse the code links are not up here, they're down here. That was confusing to me. And then what else do we have before I completely run out of time? There's the Ethernet thing. Here is the AES implementation. Should we browse the code? Yes, if we can. And then what are we missing? Nothing. All right. So we do get some code. This is the code for the Ethernet thing. Can I see it? I think trunk is where you want to be in Subversion. And it's being very slow. Okay, here we go. We have hardware, software. Let's move this into its own tab. Process.sh. I'm guessing I want hardware. Slow, slow, slow. Where did AES go? Did I accidentally close it? All right, these will be the two code thingies. All right, in the Ethernet, we have layout, MSIM, and source. I don't know which one is which. I'll try opening them in new tabs. And this is hopefully AES. We have RTL. That's where you want to be. I don't know if I can just download all this code. Is it possible? It seems to work. I'll have a local copy. Let's just check it out. And let's check what DeepSeek has to say about, what DeepSeek has to say about cores. About slowness, I mean. There are several reasons why you might not want to operate at maximum possible clock speed. Timing constraints and signal integrity. Maintaining the signal integrity becomes more challenging. Crosstalk reflections, electromagnetic interference, etc. Timing margins. They reduce the timing margin for setup and hold times. Power consumption and heat dissipation. Read latency and synchronization. At higher clock speeds, the read latency in terms of clock cycles might increase, which could complicate the design. Synchronization. Higher clock speeds can make it more difficult to synchronize different parts of the system. Design complexity, verification. Okay. Sounds like there are lots of good reasons. You can get rid of this old stuff. think this is from the RockM stream. We have two things called trunk. I mean, we have one thing called trunk, but which one is it? I don't know what happened to the other thing I checked out. Did it overwrite trunk? Hey, thanks. Mohammed says they always dealt with these as very low-level black box. It's nice to have stream such topics. Yeah, I appreciate it. I've never, like I've said before, I have no idea about any of this stuff. This is my first time really exploring any of it. And I'm sure that comes through for people who know what they're doing. And I only have a few minutes to look at this code, but let's do it. This is the AES one. I was kind of hoping to do the other one. Let's try Sreyan checkout again. This tiny AES. Where did the other one go? Oh, I have two tiny AESs. That's not what I want. This is the Ethernet one. No, my background is not hardware. My background is software. And really, my background is math. So I'm just kind of like flying pretty blind here, to be honest. But I mean, I understand the logic. Okay, so here's the, supposedly, here's the, what is TB? This is the Ethernet thing. BFM host TB. The company engineer is IK. This chat seems to be behaving better graphically. Can I scroll down? No. I need a better chat setup. Go there now. All right, you're not going to. Timescale. Let's see if TB is a thing I should know about. I don't know. Let's ignore TB. Go back to RTL. We have this tri-mode emac export, microb top V. And I don't know how this is laid out at all. We have some clock stuff. You can look at the modules. And all we have is the micro top B. We have this transmission FIFO stuff. Reset N. Something about resetting. Maybe GTX reset N. G transmit. Let's just hand this off to DeepSeek. What does this do? What does SV do? What is SV? I don't know. System Verilog probably. Here's the tri-mode emac. We have some XML, some SW, and C. So there's some C stuff, there's some data, including Tickle, I guess. And what else? XCI, I don't know what that is. Some more XML. This is maybe some sort of UI or some sort of description. Spirit, user V, library. So that we've got a vendor, a library, TME Mac, a direct connection, whether it's a direct connection, whether it's addressable. This is some sort of metadata description, I guess, of the project. Whatever. So here's, it seems like TB folder has some interesting stuff. The timescale is maybe 1 nanosecond over 1 picosecond. What does that mean? I don't know. This is some module. Do we have multiple modules? I'm not sure. We have different tasks. I don't know what a task is in System Verilog. But this is maybe testing stuff. Host initial, host delay, host final. Yeah, I don't know. ETH host BFM. The input is IARST and all of this stuff. Yeah, I have no idea. I have no idea what any of this stuff is. Okay, so let's see what DeepSeek. I feel like DeepSeek is always too zoomed in. Let's see what DeepSeek has to say. It defines a top-level module called MicroTop that integrates several components to create a system-on-a-chip design. It includes a MicroBlaze processor, Ethernet MAC, media access control, clock generation reset logic, and interfaces for LED, UART, and RGMII, reduced gigabit media independent interface. Oh, I have to go in 3 minutes. Okay, so this is defining the microb is what? MicroBlaze, I guess. And we've got some inputs and outputs, including the things like reset, UART, and RGMII. And this is the clock generation, it says. Example design clocks, example clocks. We have clock in P and N. I don't know what those are. I guess a global reset. DCM locked. And whatever the above G's are. So GTX clock above G is a 125 megahertz clock for the Ethernet MAC. So that's the Ethernet part. There's a reference clock that goes faster than the Ethernet clock. And then there's a slower clock for the AXI bus used by the MicroBlaze processor. I don't know why these are called buff G. And then reset generation generates synchronized reset signals for the different parts of the system. And so I guess this is the global reset, and you're going to somehow send resets to the other parts, because this is like a system on a chip and it's got different like subcomponents, I suppose. And then this is assigning stuff. And here's the MicroBlaze design. What is MicroBlaze? MicroBlaze. Okay, it's an AMD processor of some sort. A flexible and efficient soft processor. What makes it soft? Is a soft microprocessor core designed for the Xilinx field programmable gate arrays. Does that mean it's a like a software that can be wholly implemented using logic synthesis? So let's see if we can find the MicroBlaze. Yeah, I think that means it's written in software. This is like a library or something. And this is maybe all of this stuff probably has some meaning in the context of Xilinx or this particular MicroBlaze thing. So we have 100 megahertz AXI clock, some reset stuff, some LED stuff, and so on. And then it ends the module. Okay, I have to go. Can we install and use DeepSeek in the United States? Yes. If you have the hardware or the funds to rent the hardware, you can in fact use the whole. You can do the full version of DeepSeek. They also have the distilled models, which you can run locally on machines with much less power, but they have many fewer billions of parameters. I've done both. The full model is nicer, but I don't have the infrastructure to run it, I think, regularly. So, but the distilled model is also nice. All right, I got a jet. I'll be back tomorrow. We'll take a closer look at some of this stuff. I'm feeling like this, these OpenCores stuff, I'm not really understanding what's going on as much as the smaller greenfield projects. I don't know if we'll continue looking into these, but we'll look at something chip related tomorrow. And then, like I said, I'm behind on the doing the request thing, so I'll have to get back on that horse. Probably next week, I'll have time to look into it and see if I have any request debt that I need to pay down. So that's all for now. Thanks for joining.